Welcome back to this NPTEL online certification course in molecular rearrangement and the reactive intermediates. In the last class, I started talking about the organoboron chemistry. So in this class, I am going to talk about the one of the important reaction called the hydroboration. Correct? I already showed you the reaction in the last class, but in this class, I am going to show you several example of that. And also the other important aspect is what are the different protecting group for the boron. So you have seen only the pinnacle, correct? What are the other different protecting group for the boron? And what are based on their structure, their stability can be also varied. So let's go through them. So let's talk about some of the first thing, some of the synthesis of this different type of boronic esters, and then we want to learn about their structures of the different protecting group and then their stability, and then we are going to talk about some of the multi-boron compounds, and then the majorly trying to focus on the hydroboration reaction. So here you can see here, this is a easy method. I think I told you in the last class that one of the very easy method, that if you have a boronic acid and if you take some sort of a diols, or there are of course there are more variation. You can see there are several different diols. It could be ethane diol, like a butane, catechol, and then you have this 2,3-dimethyl butane. You can see what is happening from the butane to 2,3-butane. You can see slowly the steric is playing an important role here. Then there are some chiral diols. Okay, there are 2,2-dimethyl propane 1,3 diols, and then of course there are other chiral diol as well. Okay, so this is a very easy reaction. As I said, if you take the boronic acid in place of diethyl ether and molecular shifts, which can take this 2 equivalent of water, you can form this boronic ester. But the question comes, depending on this diol, your stability will be varying. Why we are talking about stability? Because if you are forming a boronic ester, you have to understand that in that particular compound, by taking this compound, you might want to do some other transformations. At the time, if your boronic ester is unstable, then you cannot do multiple transformation using this organoboron compound. That's why we are quickly going to learn about their structure and stability. So one of the important fact here, that if you have this cis 1,2 cyclohexane diol versus you have trans 1,2 cyclohexane diol, what is happening? In case of trans, we are seeing that it can able to form this corresponding boronic ester comfortably, but once you have this cis diol, by looking into that, you might think, sir, I think this looks cis, they can form bonds, but that is not the fact. Okay, so this is going to form an unfavorable unfavorable the boronic ester geometry. Okay, so that can be explained from the basic stereochemistry background. So by looking into this structure, you just cannot be thinking, okay, these are two OH in the same site, but that is not the fact. Once you try to draw them, suppose here you have this cis 1,2 diol, correct? So if you try to draw them from cis, then one of the OH will be axial, another OH will be in the equatorial, correct? You can do a ring flipping. So here you have one will be axial, another will be equatorial, correct? But in every cases there will be one axial, one equatorial, correct? Now if you try to form a boronic esters from there, you will form a strained unstable ring. Okay, in both the cases you end up making a strained unstable ring, correct? And then if you do another sort of a ring flip, just to try to make them in the board shape, you can able to make them in the board shape, try to put them two OH in the same side, but that is going to make again highly unstable board conformer. Okay. So what you are seeing here, that once you are sees that you are forming this strain type of unstable ring, but once they are trans, then that could be two diaxial, or they could be both equatorial. Sorry, so there will be both axial or both equatorial. Okay. So now you can see here, once they are both axial, this will be strain unstable ring, but once they are both equatorial, now they can form a very stable boronic ester. Now you can see here that there could be different boronic ester, as you see from here to, in this case, once you have this pinene 1,2 diol, what you are seeing here, the steric around this boron is getting increased. So once you see that you can see, if you compare this one versus this one versus this one, so if you coming from here to here and from here to here, you can see the steric environment around the boron is getting increased. Because what is happening, why this why the boronic ester become unstable, because you can able to, so they are going to cleave this, this boron oxygen bond through some sort of a trans esterification. That means now you can do some sort of a trans esterification. That means we have one ester. Now you can bring some another alcohol, like 1,2-diol, not alcohol, 1,2-diol, which will be forming a more stable boron ester. Then they can replace the less stable boron ester into a more stable boron ester through a trans esterification reaction. So what we are seeing here, so that is also depending on the stability, clearly depend on the environment surrounding these organoboron compounds, because if it is sterically hindered, then it will be very difficult for the nucleophile to approach to the boron, correct. So that's how you can see here, by going from this one to this side in this direction, we are seeing the stability is getting increased. Okay. So that's why this is the one getting the more stable compared to this. Okay. So that can slow down the hydrolysis. Okay. Now the question comes, if you try to compare between these two. Okay, one is the pinnacle boron ester, another is the catechol boron ester. Now why we are saying this, this is more stable, but this one is less stable. So if you think about both this alcohol, you can see here you have this oxygen layer, lone pair is there on the oxygen, it is not available for the back bonding to giving to the aromatic ring, because here, because it is a resonance stabilized compound, this kind of catechol, the oxygen lone pair is also getting involved in the phenyl ring, okay, through the resonance. So that can participate in the resonance. So that means when it is forming the boron ester, the lone pair in this particular scenario is completely given to the boron, okay, forming a very stable bond. But once you have this case here, in case of catechol, that is not there. That is one fact. The other fact is, in case of this, the pinnacle, you have this tetramethyl group, correct. So that is also forming a more steric environment compared to catechol as well. So now what happened after that, that type of diol, from diol there are so many other type of boronic ester group was developed. So the idea is that after giving this oxygen, to stabilize more, can we bring another sort of a some sort of a Lewis base atom which can give the lone pair to stable the boron even more. Okay, so that brings to the nitrogen into the picture. Okay, so that kind of bring, now you have see the boronic ester which is forming, which is now getting really stabilized more, because not only there is 2 oxygen, there is also a nitrogen which is giving electron density to the boron. Okay. So these are even more stable compared to this compound. Not only that, if you think about the pinnacle, also compared to them also, these are more stable. And that slowly brings to the discovery of a compound called N-methyl imidodiacetic acid, or a MIDA. Okay, this is a better protecting group which can even stabilize the boron. Okay. And then there are other group like DAN, where instead of 2 oxygen, you have this 2 amine here, which can also form the boronic ester by coordinating with these 2 nitrogen atoms. Okay, so we have learned about first part, that what are the stability of different boronic esters, correct. But now we are going to talk about the very important reaction which was discovered by Professor Herbert Brown, which is called the hydroboration. So if you have a olefin, as I mentioned, and if you treat with the BH3, what is going to happen? It is going to add to the corresponding olefin, okay, and then it is going to first add, and then it is going to add again and again to form this trialkyl boron. Again we are going to come back to the addition, what type of addition is happening in this reaction, we are going to come back to that in a minute. So this reaction is not only happening to olefin, it can also happen to alkyne. Remember that it is not only happening to the alkene, it can also happen to alkyne, and you can now end up making some sort of a vinyl boron compound. Okay. So you can see the boron has the boron hydrogen sigma here, correct. These are the sigma bonds, and this is the pi bond. So correct. So these are the interaction happening. The sigma bond, the BH sigma bond actually interacting with this pi bond, okay, in a concerted manner to form this product. Okay. So we are going to come back to some of the is it going through a Markovnikov or anti-Markovnikov, or all these discussion we are going to come back in a minute. But before that, I think important questions we ask. So in this particular problem, that you want to synthesize these compounds. So we are talking about one of the important thing, that in this particular transformations, if you want to get to this, this product, then you have to use this hydroboration oxidation. If you try to use something other condition, like if you try to give a acid, strong acid, then it will go for a carbocation rearrangement. We have learned about those, and it is not going to form the product we want. It is going to form a ring expansion happen, a ring expand product. And now if you go for a oxymercuration of alkene, okay, which you have learned, I think you have learned before in the sophomore organic chemistry, then you end up getting to the forming this secondary alcohol. But if you want a primary alcohol here, we definitely have to follow the hydroboration oxidation. So now I am going to talk about that reaction, which is the hydroboration. If you first think about the electronegativity difference of the boron and the hydrogen, you can see the hydrogen is more electronegative than the boron. So what is happening, if you think about that the boron and hydrogen bonds, then the electron density towards hydrogen. So the boron, you can think about the boron having some sort of a delta positive and the hydrogen having some sort of a delta negative. Now if you think about when it is adding to the olefin, it is actually adding in a syn fashion. So the BH bond coming in a syn fashion to add to the olefin. But the important question we are trying to answer in this slide, that why the boron is adding to the terminal position. That means we are talking about, we are getting to a anti-Markovnikov selectivity instead of the Markovnikov selectivity. What is happening here? So if you think the boron is, as I mentioned, the boron have a some sort of a delta positive and the hydrogen have a some sort of a delta minus. Now if that is approaching to the olefin, now you can think about the olefin, you can also think about, if you have a hydrogen as a delta minus, then that is going to interact with a carbocation which is have a delta plus. Now if you think about this one versus here the hydrogen is coming, I think here there is a error, this will be a delta minus and this will be a delta plus. Now you can think over here, you are forming a delta plus or some sort of a partial positive charge into a 1 degree carbon. Here you are forming this partial positive charge in a 2 degree carbon, correct. So in electronically, I think the formation of the carbocationic character in a 2 degree carbon will be more stabilized compared to 1 degree carbon. That's why the hydride transfer will be more favorable through this sort of a tangent state, which allow the hydride to come to the internal position and the boron to the terminal position. So that end up giving you this anti-Markovnikov addition product as a favored product. Okay. That's why you end up getting to the this product, not this product. Again, the other explanation which you always say about the steric, there once the boron as it is approaching in a syn addition, so there is a steric could be play another important important role here. That means this boron with these two hydrogen, they can interact with this alkyl group in the internal position, correct. If that interaction is happening, so that can, so this then that this tangent state will be less stable compared to this one, which will be more stable tangent state, because there will be not that, because now if there is two hydrogen here, so compared to this two hydrogen and this methyl and alkyl group here, this tangent state will be more stable. So that is so what is saying that the hydroboration reaction, there is both effect, there is steric and electronic, as I explained. Through steric effect you understand that it is going to go through this type of tangent state to avoid the stirring between the boron and the group which is present in the internal position. That's why it is going to go to the terminal position. Okay. Again, this reaction happening in a concerted manner, okay, and it's happening from the same phase. Both boron and hydrogen going to come to the olefin on the same phase of the olefin. Now we are going to talk about the next part. So first is the hydroboration happened. So from here, once you form this, first it is going to form the BH2, and then the BH2 going to constantly add. So there will be, if you think about, we end up making this BH2 after the hydroboration, and then this can add to another olefin here. Okay, so what is happening? This compound can now act as a hydroboration agent. So I'm going to come back to that discussion. So that idea was further used to make some sort of a bulky boron agent. Okay. So now that can react with two equivalent of this to form this corresponding trialkyl boron. So once you have this trialkyl boron, now if you treat with H2 to NaOH, it forms the corresponding alcohol at the end. So what is happening here? So once you react with H2 to NaOH, what is happening? because from H2O2 if you take one hydrogen out, it is generating in place of NaOH, it is generating OOH minus. So this OOH minus going to attack to this. So this hydroperoxide anion going to attack to this the boron empty orbital to form this boronate complex. Okay. Now what is happening, because now this boronate complex wants to, here this R group which is here going to participate in a 1,2 migration. So this can move from the boron to the oxygen to eliminate this group as a leaving group, that can generate this Br2 and this OR, which can take part with another 2 equivalent of this hydroperoxide anion going to add here to, and then finally it will going to form this compound which is going to get hydrolyzed to form your desired product. Okay. From there it is going to get hydrolyzed to get to the corresponding alcohol. Okay. So the important fact is how this migration is happening. If you think about this migration happening, this is a migrating group here in the boron which actually interacting with the sigma star orbital with this oxygen bond. So this sigma star orbital is getting electron density, so that it is migrating here. Okay. From this group is migrating here by giving the electron density to the sigma star orbital. So the question comes, if you have a chiral center, suppose you would have done a hydroboration, you generate a chiral center. So what is going to happen? You end up seeing a retention or inversion in the alcohol product. You end up seeing a retention, because if you think about this, when this group is getting migrated, okay, because once you have this trialkyl boron, once you generate this trialkyl boron and you treat with this OH minus or H2 to NaOH, what is happening? This group is getting migrated from boron to the corresponding oxygen, correct, through giving electron density to the corresponding sigma star orbital. So here the migrating group geometry has not changed anything. It is just, so the migrating, the configuration of the migrating group remain unchanged. There is nothing happening on that carbon. The only thing is happening, it is just this bond is getting clipped, it is getting migrated from this boron to the corresponding oxygen. So not only this H2O2 only works, there is other oxidant like oxone can also able to oxidize you, or the molecular oxygen can also oxidize the boron to the alcohol, sodium peroxide carbonate, amine oxides, N-methyl morpholine N oxide. So there are several different type of N oxide also developed. You can think about, sir, how this thing works. If you have this morpholine N oxide, it can react with the boron. Now if you think about this is reacting with the boron, with the R group here, can generate this minus, correct, which can migrate here, and this group can act as a leaving group here. Okay. That's how these groups can also, the N oxide can also use as a trimethyl N oxide can also use here to act as a oxidizing agent for the boron. So here is an example. Also oxygen can be also utilized for this type of things, first hydroboration and then oxidation to the corresponding alcohol. Now the chromium reagent can be used for this, but if you use the chromium reagent as an oxidizing agent, it will not going to stop as alcohol, it is going to oxidize all the way to the corresponding acid. So if you start with this and then use this K2Cr2O7, after the hydroboration it will take you all the way to the acid. So now we are going to talk about the polyhydroboration. That means, I think the thing I am telling you again and again that after the addition, this concerted addition, it will not stop here. It will add with another one, it will go to the corresponding trialkyl boron. Okay. So and then this trialkyl boron can oxidize to the corresponding alcohol. So the question arises that can this is going to happen always, or can you able to stop to a mono after the first hydroboration? Can you able to design some sort of reagents? Because why this is happening? Because you are actually designing after the first hydroboration. You are designing a compound, you have two boron with 2 hydrogen. Because of that reason, that can also participate in another hydroboration and still it consume all the hydrogen to form this trialkyl boron. So the question comes, can you able to develop some sort of a reagent which can only have a 1 boron with a 1 hydrogen? So now those type of reagent can be used as a monohydrobonding agent. So we are going to talk about some of these. Again, I think there are several different variation was developed. One of the thing is the catechol boron, which is very reactive one. Okay. Then there are the 9 BBN or 9. So you might be thinking that how this type of reagent was getting developed. Of course, they are developed from the corresponding olefin. Okay, so from there they can this type of reagent was developed. I am going to come back to that discussion also. So there are different type of variation like the pinnacle boron. Okay, so you can see then the 9 BBN, then the thexyl boron. So this is the structure of that corresponding diboron, and then the ICP whole 2. I think we are going to talk about this with this pinene part, because this can be used for the asymmetric synthesis, and also we are going to talk about some of the diisopropanol, the campholyl boron. There are some other version we are going to talk about, like here in the next slide. I think we talk about this one, the dicyamyl boron. So this is called Si2BH. Okay, so dicyamyl boron, you can think from the structure. What is the difference we are bringing here? We are bringing some sort of a the hydrogen reagent which are bulky in the size, and we also had only one BH group. So what is the idea here? The problem is, once you use BH3 THF, lot of times you don't find good selectivity. Of course, here we still see a very good selectivity for this particular compound, but in some other cases I have not collected all the example, but there are example where you are going to see, like here particularly from styrene, you can see you have like almost 80-20. There are also example we will see a 40-60 ratio, or sometime even like just 55 and 45, because what is happening, the BH3 THF is a smaller reagent. So that's why you don't find any selectivity difference, because here is a difference. You have a isopropyl one side, you have a methyl another side. So this is, we are talking about olefin having isopropyl one side and methyl another side. Now we can see, once you change the boron to the Cl boron or the 9 BBN, means that once you bring to this bulkier boron reagent, what is happening here? Now you can see that difference of isopropyl versus methyl. So the difference of isopropyl versus methyl is now getting the predominate here. Okay. So these factors are getting the interactions getting predominant, because you are bringing a bulkier boron. So that's why the advantage is there. That's why this bulkier boron is developed for this type of purpose, where you see the selectivity will be poor using BH3 THF. Here you can see also, like for the styrene, this selectivity can be improved drastically, very high. Okay, of course it is giving this terminal selectivity, we are not changing the selectivity, but what we are showing here, we can improve the selectivity to a very high level using this type of hydroboration reagent. Again, there is an important example here. I think why, because you can see in this example, if you are using this dicyamyl boron here, for this particular cases you have a terminal olefin and you have a terminal olefin, but you have a methyl in the internal position. So this will be a very challenging hydroboration, correct, because you have to only rely on this interaction of this methyl group. If you use 9 BBN, what is happening? In case of 9 BBN, this one getting 31%, here it is 69%. So here the other important factor is the interaction of the 9 BBN with the olefin is the important factor here. But here in the other cases, we can see here this will be a 1% here, because there is a methyl group here, versus the terminal is 99%. But once you come to like the Cl boron, so you can see that is the importance of this dicyamyl boron here, because that can give you 95% selectivity in this position, and that can able to differentiate this group, that can differentiate if you have internal methyl group. That's why once people try the if you have, of course some of the studies was done to understand through a computational studies, but the thing is, if you try to do a hydroboration, you have to explore different reagent to find out the selectivity. Another important example here, how this dicyamyl boron is important. Here you can see there are so many different olefin here. Of course both are terminal, you can talk about, you can think about, but the substitution was mono versus di. Here you can see it is selectively happening only in this position to get to this product. Again you have that, here I think it's a, this is a easier version because you have an internal versus terminal and the terminal is the winner. There are some other cases, I think we try to show you that there are some cases like if you use a 3-methyl cyclopentane, 3-methyl cyclopentene or 4-methyl cyclohexene. These are a difficult substrate to deal with. Okay, some of the cases using using the diboron the selectivity is poor, but of course using the 9 dBn we can get some more selectivity. Okay, but not good. But every cases we are seeing some like so. So this type of cases, once you have substrate like these. Okay, so this is a 3-methyl cyclopentene or you have a 4-methyl cyclohexene. Okay, because the problem is like how to control the cis versus trans, because once you go for a hydroboration, now there will be based on the methyl geometry you end up forming a cis versus trans. So that is one factor. So that means now what I am going to talk about in the next part, that how the facial selectivity is important. That means if you talk about the cyclohexane or the cyclopentane, then now the approach of the approach of the hydroborating agent to a particular phase become very important. So we are going to talk about some of this in the next lecture. Okay, and then the other things what is happen. Sometimes you find out that I think we are going to talk about also about this this scenario, that in presence of heat, sometimes this after the first hydroboration, this can rearrange, this can go for a elimination, again hydroboration till it go to the terminal position. That means you started from an internal olefin and then under heat there is a process can happen that here it can first go for a hydroboration, then it is going to get out through some sort of a elimination and then again hydroboration till it is going to the terminal position. So this is saying this hydroboration is reversible in nature, and upon heating it can migrate to the less hinder position, and migration cannot occur past to a quaternary carbon. Okay, so we are going to talk about some of the example of this in the next class. Again, I think we talk about that the stability of different type of the diol here. We talk about we also talk about the mechanism of the hydroboration reaction, and also we talk about the different type of the monohydroborating agent in this particular part. So and how that was important for selective hydroboration. Again, these are the textbooks, and thank you so much for coming to the class. I am going to see you guys in the next class. Thank you.